Hi, everybody. Welcome back to Dave's Math channel. I'm your host, David Tear, and this is my continuing feature on my daily math problems, which I post every few days on the Facebook group Classical Mathematics. And the last one I posted was a couple days ago concerned M&Ms on a chessboard, and I just found this image on the web. I hope I don't get in any copyright trouble for it, but I guess this is a CGI of, or maybe it's a real chess set where the pieces look like M&Ms. But anyway, that's not really the problem. Let's just go to the problems. So here's the statement of my. So we have a bag of 100 M&Ms with the average manufactured distribution of each color. And this is well known, by the way. I think M&M Mars Company's been using this distribution ever since they started making M&Ms about 100 years ago. They have 30% brown, 20% red, 20% yellow, 10% orange, 10% green, and 10% blue. So if we had a bag of 100, you could expect 30 brown, 20 red, 20 yellow, 10 orange, 10 green, 10 blue. Of course, you're probably gonna get some statistical fluctuations. You probably won't get these exact numbers, but for the sake of argument for this problem, I'm assuming we do get these exact figures for each color. So we open the bag of M&Ms and we spill it on a chessboard in such a way that each M&M lands completely within a given square of the board. So now what we want to do is we want to show that there exists at least one square of the chessboard with at least two M&Ms, neither of which are brown. And it turns out that there's a very simple principle in math called the pigeonhole principle. This is a very powerful principle, by the way. It's very simple to state and prove, and it's pretty obvious if you think about it. So what the pigeonhole principle says, and it's easy to think about pigeons and holes. You've probably walked in downtown in a big city, and you've probably seen pigeons flocking around, and they usually go to holes, particularly if like it rains and they want to get out of the rain, they go into these holes. And what the pigeonhole principle says is if we have n pigeons and m holes, where n and m are positive integers, then there has to exist at least one hole with at least a ceiling of n over m pigeons. And ceiling just means the nearest integer greater than n over m. So it's the next integer that's larger than n over m. N over m doesn't have to be an integer. If it is an integer, it's just equal to n over m. If it's not, it's the smallest integer that's greater than n over m. That's what we mean by the ceiling. So how do we prove this? This is a very simple result to prove. Just think about the average. The average number of pigeons in each hole, the mean, if you like, is n over m. That's just the definition of a mean. So if we could split up the pigeons and put the exact same number of pigeons in each hole, you would get n over m in each hole. Of course, if n over m wasn't an integer, you'd have to divide up one of the pigeons, which wouldn't be a very nice thing to do. But if we're keeping integer number of pigeons, then I think you can see that at least one of these holes has to have the ceiling of n over n pigeons, because that's the smallest integer that's greater than the mean, and we have to have at least one value that's greater than the mean if the mean is not an integer, right? If you just think about that, that should make sense. I mean, the mean's the average, so you have to have some values that are bigger than the average, some values are less than the average, unless everything is equal to the average, which it can't be if n over n is not an integer. So that's the proof. Pretty intuitively obvious proof. And even though this is a very obvious result, it's actually a very useful result for a lot of math problems. I've seen a lot of math problems where if you don't use the pigeonhole principle, it's almost impossible to solve. And I think this is a good example of that. So you really have to use the pigeonhole principle, I think, to solve this problem. So now replace pigeons with M and M's and holes with chessboard squares, and we have since we're 100 M and M's altogether, we said 30 of them were brown. that means 70 of them are not brown. And those are the ones we care about. So n equals 70. That's the number of pigeons. We're just replacing pigeons with non-brown M&Ms. And I think you guys all know that there's 64 squares in a standard chessboard, 8 by 8. 8 times 8 is 64. So n is 70 and m is 64. And that means by the pigeonhole principle, there has to exist a square of the chessboard with at least a ceiling of 70 over 64, which is equal to 2. So that's the proof. Very simple proof. Just using the pigeonhole principle. And that completes this problem. So thank you for watching along with math, and I'll see you guys next time.